A very good morning to all of you. I'm Dr. Akansha Singh from Bennett University, and I'll be presenting our recent work on quantum machine learning for satellite image classification. This research was done in collaboration with Dr. Krishnakant Singh from Delhi Technical Campus, and our focus is on improving robustness and efficiency in land cover classification using EuroSAT data. So before starting with the method, we should first see what is the importance of satellite imaging. Satellite image classification is critical for land use planning, disaster response. It is also important for urbanization and environmental changes, which makes accurate classification of satellite images vital for timely decisions. However, existing models often face challenges such as limited label data, high noise, which reduce the accuracy of these classification, and thus new methods are required which could improve the satellite image classification performance. The major research gap that we found while addressing the classical machine learning algorithms, we found that classical machine learning methods struggle with the lot of data related problem, and these traditional machine learning methods like CNNs and SVMs perform well on clean data, but if the data is noisy or there is low sample condition, the data becomes the performance degrades. And because of this, quantum machine learning or QML provides a promising alternative by using quantum principles like superposition and entanglement to encode richer feature spaces. Our goal is to explore whether hybrid quantum classical architectures can outperform purely classical baselines in robustness and accuracy. The core concept of hybrid approaches is quantum machine learning. Quantum machine learning combines classical neural networks with quantum circuits. In particular, we use variational quantum circuits where parameters are trained using classical optimizers while the circuit runs on simulated quantum hardware. This hybrid loop enables us to harness quantum advantages while keeping computation practical with current hardware limitations. Um, the related work, if we see from the literature, we find that prior work by Sebastian et al. Demonstrated the potential of quantum convolution neural networks, which are also known as QCNNs, for small scale image data sets. Then Otto von Batar and Datku explored parameterized quantum circuits for improved learning efficiency. And recently, we have seen that Zollner and colleagues combined autoencoders with quantum classifiers for better feature preservation. These studies highlight the growing evidence that quantum models can complement classical architectures effectively. If we go to our proposed architecture, this is the diagram which shows the proposed architecture. In the proposed architecture, we see the method is a hybrid CAE and VQC pipeline. In this pipeline, there are four key stages: data preparation and feature extraction via convolutional autoencoder. Then we have quantum data encoding, and which is followed by variational quantum circuit design and measurement and classification. The hybrid structure ensures efficient feature compression and quantum enhanced classification performance. If we look at the diagram, the input image goes into a convolutional encoder, which converts it into a latent vector. This latent vector, further, we perform quantum data encoding on this, and the angle encoding is used in this particular paper, which is given to a variational quantum circuit. The variational quantum circuit once performs the operation, then we perform the measurement. Measurement is basically the expectation value, that what value we are getting from the VQC. Once that value is calculated, we calculate the probability, and by applying threshold, the classification is done. And in this paper, we have limited the classification to binary classification. Thus, whatever is the input, we get the output labeled as either annual crop or C lake. The dataset samples, if you look at this particular image, these are some of the dataset samples. The first row shows annual crop samples, while the other second row shows sea lake. And the annual crop category contains textured agriculture patterns with color and shape variation across fields. The sea lake class includes water bodies that are visually more homogeneous but can resemble dark soil or shaded regions. The proposed method was applied on these kind of images, and when we applied this, we saw that there are some classification results that we got. The proposed QCNN VQC achieved 90% accuracy, which is close to the performance of the SVM baseline and superior to logistic regression. However, when we evaluated with more robust metrics such as F1 score, AURC, and AUPRC, the quantum model clearly outperforms the classical baselines. Table 1 shows the performance comparison of the two classes, annual crop and sea lake, and we can see that the proposed method achieves good precision and recall values for this. And similarly, we also computed the per class classification report, and we found that as compared to the um, existing methods, the QCN and VQC outperformed their performance, and the results we found were much more improved as compared to the other methods. If we look at the performance metrics, the QCN and VQC achieved 90% accuracy, which surpassed the classical models. The F1 score was 0.9428, which indicates there was a lot of robustness in the method. And the AURC is superior and it showcased enhanced reliability in classification. We also had some more parameters that we calculated. So, like table 3 shows the parameter efficiency, where we see that the baseline models, which are the classical machine learning models, they have a parameter of 181 and the accuracy is 0.861. And if we compute the accuracy per 1000 parameters, we found that in baseline models it was 0.867, whereas the QCN and VQC shows a great improvement over that, which is zero point 0.9. Similarly, the calibration results also we see. So, in case of clean data, the accuracy of MLP methods is 0.939, whereas QCNN is 0.911. Whereas, if you look at the accuracy, the QCNN shows improvement over this. And the drop also we see there is a significant drop in QC and VCC. The robustness to noisy labels also, if we see, in that case also we see there is an improvement. And the hybrid model offers efficiency advantages. We also see with only 144 parameters compared to 181 in the MLP baseline, it achieves higher accuracy and maintains stability under 20% label noise with less than 1% performance drop. This demonstrates that the promise of quantum assisted architecture for lightweight also, and it is robust also. Next, we also saw the latent space utilization using the TSNE plot. This shows that how the autoencoder effectively separates the latent representation of the two classes. Clusters are distinct, confirming that our CAE retains semantic structure before quantum encoding, and this validates our hybrid approach. Classical features are well prepared for quantum processing. We also saw that there are some misclassifications, and these misclassifications, if we see, for example, in some of the images, we saw that the true value was a sea lake, but actually an annual crop was detected, and similar kind of cases were there. So many errors involve visually ambiguous regions such as crop fields adjacent to water or dark soil patches resembling lakes, and these cases highlight the inherent challenge in visually separating classes rather than a fundamental model limitation. That is why we got these misclassifications. If we look at the key findings, we saw that there was a high recall, there is noise tolerance in the performance, and parameters are also low. So, all these findings tell us that. The QCVNN is has a high recall rate, and it is remarkable. It has a remarkable noise tolerance, and the computational feasibility is also there because the number of parameters are low. So, to conclude, I would say that this paper presented a hybrid quantum classical pipeline for land cover mapping using the EuroSAT dataset. The proposed QCNN inspired VQC classifier achieved 90% accuracy and a best threshold F1 of 9.9428, while delivering superior AUROC, AUPRC, and high recall for C-Lake class. These results demonstrate that hybrid quantum machine learning approaches can not only be competitive, but they can also be sorry, not only competitive, but they also have high parameter efficiency. And in future, we plan to improve these method to more number of classes instead of just two classes. We want to increase it for around 11 classes. And thank you very much. Thank you for listening. In case you have any questions or queries, you're most welcome to ask.